Hello, and welcome to our webinar on simulation and Markforged. So, accelerating manufacturing and strengthening your results. Let me introduce myself. My name is Changping Liu. I'm a senior technical representative at SolidExpert. So, my role is mainly to support our clients in finding solutions. So, I focus mainly on our analysis solutions, specifically simulation. I am here with Lillian Beatrix.
Hello, Chengping.
Hello, Lillian. So Lillian is our solutions expert who focuses mainly on additive manufacturing and 3D scanning. So there we go. Without further ado, we'll move on to our game plan for the webinar. First, we'll talk about the objective, what led us to present this webinar to you. So, in which we'll also talk about the challenges encountered on a racing vehicle. So what led us to look for a solution? Namely, the design and flow analysis of a reinforcement part. That's what we'll see in the second step, in order to first try to optimize the geometry of the part and to find the necessary forces for the next steps, because we'll then move on to manufacturing. So the third step, additive manufacturing with Markforged, in which we'll try to find the best parameters for the printing direction. And then, perhaps, the long-awaited moment, simulation, directly with Eiger simulation, to help us find the best choices for printing parameters. So, there you go, Lillian. I'll let you continue with the objective.
Thank you. Hello, everyone. Now, I'm going to present the objective to you a bit, and where it all started. In fact, it all began on a racetrack. For those who don't know, our president also does racing, car racing, and SolidExpert sponsors several race cars. One day, a driver came to see us, informing us that he felt a difference between the left side and the bottom side. Following analysis and several tests, we realized it was the splitter, the part at the bottom of the car that actually collects air, which was in fact defective, notably because it had come loose a bit more on one side compared to the other. So we implemented a solution, a part, to reinforce the attachment of this splitter on the left and right. This solution can be seen on the white car at the bottom left and bottom right. And in fact, it was 3D printed to reinforce its attachment. We performed an analysis, notably with flow simulation on it, which optimized the shape. Then we manufactured it, similarly optimizing the manufacturing process. So I'll hand the floor back to my colleague Chengping, who will now present the flow analysis with flow simulation.
Thank you very much, Lillian. So we're working as a team here, so I'm going to find some parameters that will help you with your structural analysis later on. So the second part is the design and flow analysis. So what we're looking at here is, well, first, the goal of this step is to manage to optimize the geometry, meaning the shape of the reinforcement part we have here, and then to find the drag forces that will correspond to the loads applied to the structure. So we're going to try right here to minimize that drag force. And well, what does that amount to here? It amounts to simply performing a validation of the design. Okay, so these are like virtual tests that we'll perform instead of having a prototype and running physical tests on it. So the solution, well, it's to run a fluid dynamics type of analysis. Okay, so we'll be able to calculate the trajectories afterwards. And speaking of optimization, well, we're going to run what we call a design study here to test different designs so that we can find the best configuration of parameters to use to get the ideal design. So the solution used for fluid dynamics, well, it's flow, simulation from SolidWorks. So let's see flow simulation in action. It's very simple here. It's as if first, flow simulation is directly integrated into SolidWorks. So we need to create an analysis here. We'll start the equivalent of a wizard here that will go through all the important functions of a fluid dynamics analysis, the boundary conditions, what fluid or fluids are used, the units, and so on. Okay, so in a few clicks, we managed to define the essential functions here. Okay, so what we have here is a vehicle traveling at 200 kilometers per hour with a 100 kilometer per hour wind. So that's why we entered 300 kilometers per hour earlier. What are we going to ask for here? Define the forces, okay, drag forces, as we just selected on the screen. So we want feedback from the software on these results, but it doesn't stop there. It's not just single results we can get here. We can even use an equation, okay? An equation that will allow us to calculate, for example, a pressure differential. I could have even said an equation that simply calculates a drag coefficient. The mesh. So the mesh is an essential step in this analysis. It might seem complicated, but it's actually very simple. Okay, look here. With functions, to preview the mesh, we can more easily detect which parameters to use in a given situation. Okay, for example, the wall of the part here. So I should maybe set a refinement level of 3 or 4. Then we start the calculations. So whether it's on my own workstation or one connected to the network, by using all the cores of my computer, we then manage to get results. So there you go. The first thing we should do is verify that the analysis was set up correctly. We often say garbage in, garbage out when it comes to these analyses. So we make sure the flow is moving correctly. Using a trajectory plot, okay, as we can see here. We mentioned earlier, right, that the drag force is a result we wanted to calculate. So here we go. We're going to look for the forces, so about 14, 15 newtons there for the drag force. And since we're running a virtual analysis, why not run several tests? Okay, like we were talking about earlier, the design study. Why not vary a radius? Okay, the radius on the front part of the piece. We could have used the thickness of the piece or maybe the angle of the piece. Okay, so by varying parameters, we can obtain several scenarios. So here, it's about automating the creation of several scenarios so we don't have to process them one by one. Okay, so we're looking for a lot of productivity this way in order to minimize in drag force. Perfect. So this will allow us to get the forces to use for the next step, okay, for the structural analysis. But first of all, flow simulation will have allowed us to ensure the quality and performance of our product, okay, even before launching into production. It'll allow me to reduce costs as well, right? So prototyping costs, right? Rather than creating endless physical tests. Why not run it virtually and we'll achieve the objectives on the very first try? Optimization. Okay, so we're optimizing the design. We talked earlier about optimizing the geometry or simply the shape of the piece. So by having a tool like the design study, we can run several tests using a table. So we're automating several scenarios that way. And all of that translates into a shorter time to market, quite simply. So what are we going to take away here to stay conservative? Okay, we're going to take the worst case scenario we obtained. So we noted here, following our tests, that the wall representing the bodywork contributed a lot to reducing the drag force. So we're going to take the worst case, which is a safer case. So that corresponds here to the case where we have the piece as is, without the bodywork wall, so with a drag force of about 20 newtons. So from here, well, I'll take these results and hand everything back to you, Lillian.
Thanks, Chengtheng. So from there, we now have a good idea of which parts we'll need to manufacture and the stresses acting on them. So as a reminder, actually, we set ourselves a few manufacturing goals. The first is to withstand a force of 40 newtons, which is the force applied by the wind, with a factor of 2 on this force. Next, we also want to withstand a vertical force representing the splitter load of 25 newtons per screw, so 50 newtons in total. Finally, we want the entire part, as a whole, to have a safety factor greater than 2. So from there, we're going to select a manufacturing method. Here, we chose additive manufacturing, specifically with our Markforged printers. The reason we chose this method is because it allowed us to have prototypes to use on the cars as quickly as possible, and with a relatively low cost per part for a small quantity of parts. Considering we only have 3 cars that actually needed these reinforcements, So from there, we load our part into Eiger in the same position we simulated it in. And we're just going to save it so that the software calculates the details, like the cost, the print time, and so on. These aren't the most important data points here. Actually, we'll mostly keep it for the orientation and go straight to defining our load case. Here, Eiger offers 3 ways to fix a face. The first is with a fixed support, as seen on the top screws, symbolizing the attachment to the bodywork. The second step is, well, the second fixation method is a slider, where movement in 2 axes is free and normal movement is blocked. We're blocking 3 planes here just to stop our part from moving on an XY plane, but not in its height. And we apply the forces on the height, 25 newtons, to represent the splitter load. So here we can see our part where we've applied all our forces, including the wind force on the entire part. The 225 Newton forces on the splitter, the fixed support at the top, and the sliders at the bottom. To block our transverse movements, we save our validation and our load case. And now this save will apply to the whole part, even if we change its orientation. The next step here will be to find the print direction for a part. As you might know, a 3D print isn't actually the same in all directions. Indeed, the height axis, the z-axis, will be weaker than the other 2 axes. This comes directly from the printing technology and the layer-by-layer adhesion versus within the same layer. So here, we're going to try to see what the best print direction would be to keep the weakness of the z-axis on the axis that is under the least stress. So we're going to run a simulation, specifically vertically, and compare it here with other positions. So here we can see the vertical safety factor is 0.94 and a cost of 10.89. The values aren't the most important thing here. They'll mostly be used for comparison. So for example, when we place the part horizontally, we see that the safety factor increases by 56% to reach 1.47. That's a significantly large increase for a cost that remains relatively similar at $11.06, which is an increase of only 1.5%. So from there, we've determined our best print orientation, which is horizontal. We're going to re-simulate our part, but this time to define the choices and select our print parameters, like what infill we'll use, where we'll place the fibers, how many wall layers we'll have, how many floor and roof layers, and so on. So from here, we put our part back into Eiger in the new position, horizontal, and we'll go to the Simulation tab. We'll obviously validate that we still have the same safety factor we saw earlier. And now we're going to use an option called Optimization. This option will calculate different print parameters, different infill settings, as I mentioned, fiber placement, and so on. And it will give us results. So here, we can see that Eiger found a solution where the safety factor could exceed 2, specifically by adding fibers. So we'll take a look at the solution it proposed with the fibers and click on Apply. So here, Eiger will recalculate the part and automatically apply the fiber placement, where it achieved a solution above the safety factor we set, which was 2. So now we can see what Eiger did and the fiber placement. It's not necessarily ideal at this stage. We can see that the fiber layers are stacked right on top of each other. Fiber-to-fiber adhesion isn't as good as fiber-to-onyx, so we're going to slightly modify the placement to add a layer of onyx between each layer of carbon fiber. And we'll also space out our 2 fiber groups to place some as far top and bottom as possible to create the strongest sandwich panel possible. So now we can see that the onyx layer has been correctly applied between the 2. We'll do the same for the other fiber group. We're going to modify it. And in the end, we get a result where the fibers are placed exactly as we wanted. We can see it here. Still, perfect. So now we'll validate this solution again with simulation to ensure we have satisfactory results. So here we can see we've reached a safety factor of 2.18, which is above our goal of 2. As for the cost, it remained similar or even lower than what optimization suggested, with a manufacturing cost of around $30. So if we compare it back to the optimization results, we see we have a higher safety factor than what was proposed, for costs that are also lower than what was previously suggested. So we have a solution here that meets all our criteria with the minimized cost. In summary, simulation allowed us to simulate several variants and compare them, whether to find the print orientation or the parameters. We were able to optimize our various printing parameters to reduce costs and maximize the strength of our part. In short, it allowed us to save time and money. I'll hand it back to Changpeng, who will conclude this great project in this great webinar.
Thank you very much, Lilia. Wow, what a great way to wrap it all up with Argus simulation. It's really impressive how we can facilitate this whole step of comparing printing parameters. So there we go, we've reached the end. So to recap our webinar, we started by talking about the challenges faced with our president's race car. And the solution was to design a reinforcement part, okay, without impacting the vehicle's aerodynamics. And it doesn't stop at design. We also have to manufacture the part. So it's a series of steps we have to perform here, including flow analysis, okay, to allow us to optimize the shape first, optimizing the part's geometry, and then finding the structural loads to take those values and plug them into Argus simulation. And it was thanks to our SOLIDWORKS flow simulation solution that we managed to create the fluid dynamics analysis. Then it's simply importing into Markforged's Eiger, where we were able to identify the ideal printing direction, okay, sort of as a preliminary step here, to then perform a more complete simulation analysis directly in Eiger, still with Markforged, in order to simply optimize the 3D printing parameters. Okay, so a great way here, using certain parameters that we'll enter, to get the equivalent of a table to automate several 3D printing tests, to find out, for example, which parameter will allow me to get a lower cost part, or simply, what's the best material to use? Okay, is it just onyx, or should it be reinforced with fiber? So finding the best combination of printing parameters, and there you have it. So if there are any questions, don't hesitate. You can always leave us a thumbs up, okay? And then a representative from Solid Expert will get back to you shortly to start a discussion or simply answer your questions. Thank you all for watching the webinar. Thank you, Lilia.
Thank you, Chengpin.
Let's stay in touch, and you can always find us on our Solid Expert social media channels as well by scanning the QR code you see on the screen. Thanks again, and see you next time.